Now we were dealing with the problem of cantilever slab in the last lecture. Okay, so the live load on the slab was 3000 Newton per meter square. The span of the slab, the length of the slab, it is given as 1.25 meter in the numerical. M20 grade of concrete is there and Fe415 steel. So we have calculated the depth, and that is 130 mm effective depth, and we have provided 150 mm overall depth. Okay, after that we have calculated the effective span, which is 1.315 meter. Okay, after that we have done the load calculations. So we have calculated the total load of 11.6 kilonewton per meter. Then we calculate the bending moment, and after that we have taken the check for depth, and we found that the required depth is near about 60 to 65 mm, and the provided depth is 130 mm. Okay, so check for depth is over. Now we will move to the further step, that is steel calculations. Now we will do steel calculation. Steel calculations. So the formula to calculate the steel is AST is equal to 0.5 FCKBD upon Fy in bracket 1 minus under root 1 minus 4.6 mu upon FCKBD square. This is the formula. Now put the values in the formula and find the answer. So AST is equal to 0.5 as it is, FCK is 20, B is 1000 per meter width we have assumed, into D. What is the depth? It is 130 mm, whole divided by this, whole divided by 415 here in bracket 1 minus under root 1 minus 4.6 into mu. The value of bending moment was 10.05 into 10 to the power 6 divided by FCK is 20 into B is 1000 into D square, again 130. All the values, please cross verify the answer, is this correct or not. It works out to be 222.09 mm square. This is what is the answer. Okay, and one more thing is that today, now due to Wednesday, there is electricity problem, so college internet is not working, so there may be the interruptions in between the lecture. So in between the lecture, if my voice is not audible, then you can tell me through chat. Okay, so now AST is 222.09 mm square. So after the calculation of AST, we will assume for slab 10 mm diameter bars as a main steel reinforcement. Okay, so assume 10 mm dia bars. Okay, now we have assumed 10 mm diameter bars. Then we will calculate number of bars first. So number of bars. So number of bars is equal to what? It is AST, that is 222.09 divided by area of single bar, that is pi by 4 into 10 square. So the number of bars, which works out to be 2.82 which is nearly equal to 3 numbers. Nearly equal to 3 numbers. Okay. So now, after the calculation of number of bars, we will calculate the AST provided. Okay. So we are going to provide the 3 bars of 10 diameter. Okay, just a moment. AST provided. AST provided is equal to, we are going to provide 3 bars each of diameter 10 So calculate this value. What is the AST provided now? 235.61 square. This is the AST provided. This is the AST provided 235.61. Okay. Then we calculate the percentage of steel which is provided. Percentage of steel provided. Initially we have assumed 0.3% of steel. Now we will calculate what we have actually provided. Is the formula is 100 AST divided by BD. This is the formula, which is equal to 100 into AST, that is AST provided 235.61 divided by, it is divided by B is 1000 into D is 130. So this value it works out to be 0.18%. This value works out to be 0.18%. Okay. So now here we will calculate now the spacing of the bars. After this spacing of bars. So now the spacing, you know that we will calculate the spacing by using two clauses which are given in the IS code, and one is by our using regular formula. So first spacing is equal to, first thing, spacing S is equal to, how do we calculate the spacing? Area of one bar which you have provided, area of single bar divided by AST provided, that is 235.61 into width. Now your width is 1000. Okay, per meter analysis you are doing. So if you calculate this, you will get the spacing as near about 333.34 So we will round up this value to 330 We always reduce the spacing and we always increase the depth when we are doing round up. So now the second thing, spacing. I have already told you where it is given. The clauses are also known to you. I hope now you have noted down those clauses. Still, I will tell you it is from clause number 26.3, page number 46. Okay, now you can refer the IS code. So from that we can say that spacing is equal to 3D, which is equal to 3 into 130, which is equal to 390 Okay, these spacings are always center to center. And the third thing is, in no case your spacing of main reinforcement S is equal to, it must be 300 center to center. Now we will choose the minimum value out of these three values for the spacing. So which is the minimum value? 300. So we can write over here, provide 3 bars of 10 diameter about 300 center to center, about 300 center to center. So this is your main steel. This is your main steel. Okay. So now we will calculate the distribution steel. Next step is the calculation of distribution steel. So distribution steel. Now how do we calculate the distribution steel now? I have already shown you the clause. Okay, according to the clause, if Fe415 or Fe500 steel is used, then it is 0.12% of gross area. Okay, that is your distribution steel. And if Fe250 is used, then it is 0.15% of gross area. So it is now AST for distribution. I will write over here D. This is the notation. ASTD is equal to, it is 0.12%. Okay, so it is 0.12. So I will write first 0.12%. It is 0.12% into B into D. This is the formula. Here we always take the overall depth. Now here it is percentage. So 0.12 divided by 100 multiplied by 1000 multiplied by overall depth is 150. So if you solve this, you will get the value of ASTD, and the value of ASTD is, what is the value of distribution steel? It comes out to be 180 mm square. 180 mm square. Okay. So for the distribution steel, we will assume 8 mm diameter bars. Okay. So assume 8 mm bar diameter. So we will assume 8 mm bar diameter. Then number of bars we will calculate. So the number of bars equal to, so it is ASTD 180 divided by area of single bar, which is 3.58, which is nearly equal to 4 numbers. Okay, so 4 number of bars are required. So now here we will calculate the this ASTD provided. Okay, area of distribution steel ASTD, or ASTD provided, what we are going to provide is equal to, we are going to provide 4 bars, each of bar diameter 8 mm. Okay. So ASTD provided, it works out to be 201.06 mm square. This is your, what we can say, ASTD provided. So the next point is spacing. Spacing of distribution steel. Spacing of distribution steel. So again, spacing, first thing, we will calculate the spacing by using formula. Spacing is equal to, how do we calculate this? It is area of single bar divided by ASTD, which is provided, multiplied by width. So if you solve this, it comes out to be 250 mm, center to center. Then secondly, spacing is equal to, according to IS 456 clause number 26.3, page number 46, spacing is equal to, for distribution steel it is 5D, 5 into 130, it is 650 mm, center to center. Okay, it is 650 mm, center to center. And in no case your spacing must be It should be 450 mm, center to center. So we will choose the lesser value out of all these values. So I will write finally provide 4 bars of 8 mm diameter about 250 mm center to center. And so this is your distribution steel. This is your distribution steel. So now we have calculated the main steel as well as we have calculated the distribution steel. Okay. So now after this, now we will take the check. Okay, we will take the check for shear, then check for deflection and check for development. So first, here you see that what is our percentage of steel assume. Our percentage of steel assume is 0.3%. Okay, here our percentage of steel what we have assumed, which is equal to how much? 0.3%, which is which is greater than which is greater than percentage of steel provided. Okay, how much we have provided? 0.18%. So in the last lecture I have told you already, if your percentage of steel assumed is greater than your percentage of steel provided, actually provided, then there is no need to take the check for deflection. Deflection criteria is satisfied. Okay, so as I can write as percentage of steel assumed is greater than the percentage of steel provided, hence hence the deflection criteria is satisfied. The deflection criteria is satisfied. Okay, so now out of three checks, see, for slab usually we take the three types of check. First check is for deflection. Okay, second is for development length, and third is for shear. Okay, in any order you can take these checks. Okay, there is no restriction. I can take the check for shear first, then I can take the check for deflection, then I can take the check for development. Okay, there is no such a rule that this check you need to take first while checking the things. So now usually, but what method generally followed? First, we always take the check for shear. Okay, this is in general I am telling you, there is no rule. We will take the check for shear first. After that we always take the check for deflection, and then at the last we take the check for development. But here we have found that our percentage of steel assumed is greater than our percentage of steel which we have actually provided. So there is no need to take the check for deflection, it is already satisfied. Okay, so now we have to check this slab is safer for remaining two criteria. So now after the deflection criteria, we will move further for check for shear. Okay. So now we will take the check for shear. Next step is check for shear. Okay. So now you know that shear force. How do we calculate the shear force now? So I will calculate the shear force first. Shear force VU is equal to, what is the formula for the shear force if the slab is the cantilever slab? What is the maximum shear force in the cantilever beam? Can you tell me what is the maximum shear force in cantilever beam? How do we calculate? So the check for shear when the slab is the cantilever, we take it always shear force. We always calculate it as W into L effective. W into L effective. Now you understand. You can see over here. This W, this W is nothing but it is in kilonewton per meter multiplied by meter. So ultimately you will get the unit as kilonewton, and it is your shear force which is acting. Okay. So if you put the values, then what are the values? It is 11.625 your ultimate load multiplied by your effective length 1.315. So if you solve this, you will get the value of the shear force, ultimate shear force. So what is the value of that shear force? So it is 15.29 kilonewton. This is the value of the shear force. Okay. Now after the calculation of shear force, we will calculate the shear stress, nominal shear stresses, which is actually get developed in the slab. So next is the nominal shear stress. Nominal shear stress. Okay, so this is also for the notation for this is tau v, and it is calculated as tau v is equal to vu upon bd. And this is given in this formula is also given in the IS code. If you refer clause number 40.1, page number 72. Okay, there this formula is given. I have already shown you where the formula is given. Okay, now you can refer the IS code. Clause number 40.1, page number 72. Now in this, if you put the values, you will get the answer for the shear stress which is actually get developed in the cantilever slab. This tau v, whatever we are calculating, this is called as nominal shear stress, and this shear stress is actually get developed in this cantilever slab due to the applied live load and dead load. So your VU is 14 point, how much we have calculated? It is 15.29. Okay, so the value of VU is 15.29. It is in kilonewton, so multiply this by 10 raised to 3, then divide it by BD. Okay, so per meter width is our analysis. So 1000 into effective depth, it is 130. So what is the value of the nominal shear stress? The value of nominal shear stress is, what is the value? 117, 0.11. Okay, so 0.11 Newton per mm square. So it is 0.11 megapascal. Okay, you might have known this conversion. Okay, 1 MPa, 1 megapascal is equal to 1 Newton per mm square. Okay, if you don't know this conversion, then now copy down this. This is the conversion. Okay, so 1 Newton per mm square is nothing but 1 megapascal. So I can say that our nominal shear stress is 0.11 megapascal MPa. Now we will calculate the percentage of steel at support. Okay, so now percentage of steel at support, we will calculate this. So percentage of steel at support. Okay. We can use the notation for this is PT at support. So you know that generally what we do, generally whatever the percentage of steel we have calculated at the center, half of that we always provide at the support. Okay, so the percentage of steel which we have provided, it is 0.18 for the main steel reinforcement divided by 2. So the answer is 0.09. The answer is 0.09. Now next step is calculate calculate permissible shear stress. Permissible shear stress. Now we need to calculate what is the allowed shear stress by ISO. The permissible shear stress. The notation is tau c. How do we calculate this? How do we calculate this? You can go to page number 73, clause number 40.2.1, table number 19. So I will write over here. Clause number 40.2.1, page number 19, page number 19, sorry, table number 19, page number 73. Now we will move to the IS code so that you will understand this. So now table number 19, page number 73. Previously also we have used this table. Table number 19, design shear strength of concrete, that is tau C in Newton per mm square. Okay. So here if you see, it is percentage of steel is given 100 AST upon BD. So what is the percentage of steel now? It is 0.09%. This is our percentage of steel. So what is the value of tau C now? Permissible shear stress. Now if you see M20 grade of concrete, here is the table. Okay, you need to look at in this column. So first value is 0.15, and what they have told us here, if you see, if it is greater less than if it is greater than or equal to 0.15, then it is 0.28. Okay, and if the value is less than 0.15, then you should consider the minimum value as 0.28. Okay, so this is our minimum value, 0.28. Okay, because our percentage of steel is 0.09. If our percentage of steel comes between any value, suppose now 0.55, then we need to do the interpolation between 0.50 and 0.75 to get the value of 0.55 or 0.6 if it comes in between. But now here our percentage of steel is 0.09, which is less than 0.15. So the minimum value for M20 grade of concrete is 0.28. So this value we will take over here for our further calculation. So now we will move to the whiteboard again. So here now, therefore, tau C is equal to, it is 0.28 megapascal, that is Newton per mm square. Now see, our permissible stress by the IS code is 0.28, and the stress which is developed, okay, so this is the permissible stress. According to IS code, this stress can be permitted. This much of stress can be allowed in the slab. But actually, how much stress is getting developed is 0.11. Okay, so it is safe because 0.11 is the actual stress in the slab and permissible stress is 0.28. So this quantity is greater, so it is naturally it is safe. So here I can say that your tau C is greater than tau V, so hence it is safe, hence it is safe in shear. Okay, you can write further if you want, it is safe in shear. Okay. So now this is the check for shear. This is the check for shear. Now after this we will calculate the check for development length. That is our last check. So check for development length. Check for development length. Okay. So first of all, calculate the development length LD. Development length LD is equal to, what is the formula? You need to refer the formula which is given in the IS code. I have already shown you the formula. Phi sigma s upon 4 tau BD. This is the formula. So now, what is the value of this So as you know that tau BD it is 1.2, but we need to increase it by 60% when it is provided in tension zone. So it is 1.2 into 1.6. Okay, that is the increment by 60%. So I can write over here phi is equal to what is our main steel bar diameter 10 into sigma s is 0.87 into fy is 415 whole divided by 4 into tau bd. Okay, tau bd value is 1.2 and increase this value by 60%, that is 1.6. After solving this, it is 470.11 mm. This is the development length. So we will round up this length to 475 mm. Okay. So this is our development length. Now calculate LD1. Okay. Now LD1 is equal to, what is the formula? It is 1.3 M1 upon VU plus L0. This is the formula. So you know all the terms in this formula now. So therefore M1 is equal to how much? It is MU by 2. So it is 10.05 divided by 2. So it works out to be 5.025 kilonewton meter. This is the value of M1. VU is already known to you. What is the value of VU? It is 15.23 or 29 something. No? We have already calculated that 15.29. So VU is equal to 15.29 kilonewton and then L0. Okay. So you know that L0 we can calculate it by, again there is one shortcut for L0. In IS code they told us that we need to calculate the L0 by using the clause, two clauses which are given, but you can skip those clauses as the L0 we can calculate by the formula which is width of support by 2 minus clear cover. That L0 is sufficient for this. Okay, or otherwise if you calculate the other two L0s also and you take the value from that, then also it is okay. It doesn't make much more difference. So L0 is equal to, it is width of support divided by 2 minus clear cover. So L0 is equal to, now what is the width of support? Is it given in the numerical width of support? Check the numerical and let me know the width of support is given in. So in the numerical the width of support is not given. Okay. So if the width of support is not given, then you need to assume the width. So here I can write assuming width of support. Now see the bending moment on this slab is very less, that's 10.05. So there is no need to provide the larger width supports. So we can provide the support width of 150 mm or 120 mm also. Why I have chosen this 150 mm? Because the bending moment on this cantilever slab is very less. Okay, if the bending moment is more, that is near about 15 km meter then 20 kilonewton meter or more than this, then in this type of situation you can go for higher width of support, that is 230 mm and above. So now after assuming the width of support, L0 is equal to 150 by 2 minus our clear cover. What is the clear cover? It is 15 mm. So 150 by 2, 75, 75 minus 15. It is 60 mm. So this is the value of L0. Now check, find the value of LD1. It is 1.3 into M1 is 5.025 into 10 to the power 6 divided by VU 14.29 into 10 to the power 3, okay, minus L0. So L0 is 60. L0 is 60. Sorry, not it is minus, it is plus. So if you solve this, you will get the value as 488.92. So here our LD is less than LD1, hence it is safe. LD is less than LD1, hence it is safe. Okay. Now we will draw the typical section of cantilever slab and we will show the reinforcement. So now this is our cantilever slab. Now I will show over here the support. Okay. Here is the support. So now what will happen? See, if any cantilever structure is there, suppose now a cantilever beam is there. Now I will draw a cantilever structure. Suppose now this is a cantilever beam and a load is applied on the beam somewhere here. Suppose the load is W and the span is L. Now due to this load, what will happen to this beam? Due to this load, what will happen to this beam? It will deflate like this. Okay. Suppose now UDL is also there. The self weight of the beam is UDL. Okay. Then it will deflate like this. This is the deflection shape. Okay. So in the case of cantilever beam, the tension is created at the top. Where if you see the shape, it is deflected like this. It is deflected in this. So tension is at the top and compression is at the bottom. So whenever tension is there, at whichever side tension is there, we always provide the steel to resist the tension. Concrete resists the compression. So now if we show the reinforcement details over here, then now at the top tension is there, so we will show our bar at the top. Then this will bend. up to certain length, and here also. So this is our main steel. This is our main steel. These are how three bars, no? Three bars of 10 mm diameter. About what was the spacing? We have calculated the spacing now already. How much is the spacing now? 487.27. Spacing. 300 mm center to center. Okay, so these bars are 300 mm center to center. Now I will draw the distribution street. This is our distribution street. 4 bars of 8 mm diameter about what was the spacing? 50 mm. 250 mm center. This is our reinforcement detail. Okay. Now draw this diagram quickly. After this, we will see the design of one-way continuous slab. We will see the design of one-way continuous slab. So for your syllabus, simply supported one-way continuous slab is there. Okay, two-way continuous slabs are not there for your syllabus, so one-way continuous slab is there. So the next type of slab is one-way continuous slab. So I will write down the numerical, you copy down it, and then we will solve. Design a continuous slab supported on beam and end walls, comma, the live load on slab is 3000 Newton per meter square. Full stop. Use M20 and Fe415, the span of slab, the span of slab is is 15 meter by 5 meter, consisting of consisting of 5 panels, consisting of 5 panels. Full stop. Design design the end panel, design the end panel. This is the given problem. I will read it once again. To design a continuous slab supported on a beam and end walls, the live load on the slab is 300 Newton per meter square. Use M20 and Fe415. The span of slab is 15 meter by 5 meter, consisting of 5 panels. Design the end panel. So now it consists of 5 panels. So I will draw first the 5 panels of the slab. So this is a single panel. Then this is second panel. Again third panel. These are called as panels. Then similarly fourth panel, and after that fifth panel. Okay. So what they have mentioned, it is 15 meter by 5 meter. Now if you measure this total length, this total, it is given as 15 meter. 15 meter. And then 5 meter is this length. This is 5 meter. Now how many panels are there? 1, 2, 3, 4, 5. These 5 are the panels. Okay, so all these are the slabs. Continuous slabs are there. So now in the problem they have not mentioned that what is the size of each and every slab panel, sorry, what is the size of each and every slab panel. Only they have told us 15 meter by 5 meter is the total span and 5 panels are there. So as nothing is given in the problem, we will assume that all these panels are equal panels. Okay, we will assume that all these panels are equal panels. Now if I assume all these panels are equal panels, then what is the total length? The total length is 15 meter and 5 panels are there. So each of the panel is of length how much? 3 meter. So this panel is having a length of 3 meter. This is also 3 meter, 3 meter, 3 meter and 3 meter. Okay. Now the next important thing is, see, out of these 5 panels, the panel number 1 and 5. Okay, this panel number 1 I will write over here separately. Panel number 1 and 5, panel number 1 and 5 are called as end panels because those are placed at the end. Yeah, end panels, and remaining panels, panel number 2 to 4. Okay, these are called as intermediate panels. Intermediate panels. Okay, so this panel is end panel. This is also called as end panel. And the intermediate panels are 2, 3 and 4. These are the intermediate panels. So now what they have told us, design the end panel. End panels means either you should design panel number 1 or panel number 5. And in short, whatever panel you are going to design now, Near about same steel will be there in each and every panel because all are having equal damage. Okay. So now I hope now this diagram is clear to you. So the next thing is, here the width of support is not given. So first I will assume the width of support. So assuming width of support, as this slab is the continuous slab, so bending moment will be less. So I have assumed width of support as 150 mm. Okay. Here also you can assume width of support if you want 230 mm. If you want, you can assume it as a 230 mm. Okay. So the first thing is that depth calculation. So depth calculation. How do we calculate the depth? Calculate the depth. So we know the formula. D is equal to effective depth, that is span divided by some factor is there into modification factor. In the case of one-way slab, we always will take here 20. In the case of cantilever slab, we take the same value as 7. Okay. वन वे स्लॅबला 20 घेतलं होतं, कॅन्टिलिव्हर स्लॅबला 7 होतं. आता here it is the continuous slab and we need to design the end panel of continuous slab. Okay. So now what is the depth? So again we need to go to the IS code. So IS code we will see what is the criteria for providing the depth. So now in the IS code we will move to page number 37. Open page number 37. Okay. So here now page number 37 and read this. So what does it say? The basic span to effective depth ratios for spans up to 10 meter. Okay, up to, and it is a cantilever 7, simply supported 20, continuous 26. Now see what is the meaning of span. You should not consider the span as a 15 meter. Span is not 15 meter, length is 15 meter, and that too the length of 5 panels is given to you as a 15 meter. But you are designing a single panel. Either you are going to design the end panel or you are going to design the intermediate panel, depending upon the question, what is asked in the question. So now here what they have told us, design the end panel. Okay. So for the end panel now, what factor we are going to take? This is most important. So pay attention now. This is important thing which I am going to tell you now. See here for simply supported how much it is 20. For continuous how much it is 26. Now if I show you the slab, that is 5 panel slab in line diagram, I will show somewhere here only so that you will understand. Now suppose I will draw it in a line diagram. There are two supports. Here is one support and second support is over here. This is I am talking about the slab. And how many panels are there in the slab? 5 panels are there. Okay. So one, then this is second, third, fourth. Okay, for your understanding, I have written it like this. So here if you see, this is your first panel, second panel, third panel, fourth panel and fifth panel. Okay. So now this is first panel, this is your end panel. And fifth panel is also your end panel. Now in the problem they told you to design the end panel. Now just think about this end panel now. If you see the end panel, its one end of the panel is continuous. Okay, because on the if I consider now this panel number 5, then the left hand side of the panel number 5 is continuous because after this panel 5, panel 4 will start. Okay, so one side is continuous of this panel, and if you see the right hand side of the panel, it is simply supported and it is not continuous. Okay, it is not continuous, it is simply supported. So I will write over here for your understanding. So here if you can see, this side is continuous. Okay, this side is continuous. Just a moment. Okay, so I was telling about the continuous slab, panel number 5, I think so. So again I will draw the same diagram. Now you can understand that now I will draw only the panel number 5. Now if you see, this is your panel number 5. Here the simple support is given. Here on this end the simple support is given. Now see, at this end your slab is continuous. Okay, and on other side, this side on the right hand side, it is simply supported. It is simply supported. This is I am talking about this panel number 5. This is your end panel. This is your end panel. Similarly, if you see the case of your first panel, suppose now in between there are panels are there, and if I draw now the first panel, similar thing is there. For first panel support over here, this is the support, and this is your first panel. First panel. Okay, after that, here after first panel, second will be there, third will be there, fourth will be there, and then fifth is there. So again, if you see carefully, here this is simple support, this is simply supported. Okay, and at this end now, this end is again continuous. This is again continuous. So I can say that for end panel, our one end is continuous. Okay, one end is continuous and another end is simply supported. Okay, why I am telling you all these things, why I am telling you the logic, because here in the IS code they have told us for simply supported the factor is 20, constant is 20, and for continuous the constant is 26. Okay, they have told us if both the for the panel if it is simply supported then it is 20, for continuous it is 26, and why it is required, because it is d is equal to span divided by this value into modification factor. This is our formula. Okay, so to calculate this value, now what should what we are going to take, 20 or 26, as we are having both the conditions, one end is simply supported, another is continuous. So in these types of situation, what we normally do, we take the average of these two. We take the average of these two values. So what is the average? It is 20 plus 26 divided by 2. So it works out to be 23 central value. And why we have taken this average? Because our one end is simply supported, another end is continuous. Same is the thing with this also. One end is simply supported, another is continuous. and in the numerical they have told us to design the end panel. So these are the end panels. So this is the condition at the end panel at the support. So that is why we have taken the average of these two, because for simply supported it is 20, for continuous it is 26. If you take the average, then it works out to be 23. Okay, so now this we will take while solving the problem. Now depth is equal to d is equal to, okay, so it is span divided by 23 into modification factor. Now how much is the span? Now your slab is the end slab. Okay, so it is given as 15 meter is the total length. So length of each panel is 3 meter. Okay, and from 3 meter you need to consider the center to center distance. So what is the center to center distance? If you assume the width of support as uh, what is our width of support? It is 150. See, I will draw the panel. सगळं तुमच्या डोक्यावरून जात असेल तर now this is the panel. Okay. Now I will draw the support. At the end the support is there. Here now wall is there at the end. Here at this end wall is there. Okay. Here this end the wall is there. So what is the width of this wall? What is the width of this wall? The width of this wall is 0.15 meter. Clear span from here this point to this point is 3 meter. Okay. And again here the support will be there. This is again 0.15 meter. So now the center to center distance, if you want, then it is from the center of this support to the center of this continuous support over here. So this is your center to center distance. This we need to calculate. This is your C to C, center to center distance. And how much it is? It will be 3 plus 0.15 by 2, half of the support on left hand side plus half of the support on right hand side. So this is nothing but this is your span. Okay. Now therefore D is equal to, it is 3 plus 0.15. So it is 3.15 divided by 3.15 divided by 23 into modification factor. 23 into modification factor. Okay. Now again to calculate the modification factor, we need to refer the figure number 4. To calculate the modification factor, we need to refer the figure number 4. So now, how do we will move to the IS code first. Before referring that, we should assume something. We need to assume the percentage of steel. Okay, we need to assume the percentage of steel first. So how much percentage of steel we assume generally for the slab? So for the slab, generally the percentage of steel is from 0.2% to 0.4%. So now we will assume 0.3% of steel. So here I will write assume percentage of steel PT as 0.3%. So what is our percentage of steel assumed? 0.3%. Now calculate the value of Fs. So if you calculate the value of Fs, the formula is given below the figure number 4. Okay, that value works out to be 240.7, which is nearly equal to 240. And now if you see the graph for the value of this on this 240 line, you will get the modification factor and its value is 1.4. So after that, now put all these values, put all these values in this formula and calculate the value of D. So D is equal to, what is the value of D? Roll number 66, Akshay Shinde, switch off your mic. It comes out to be 97.82 mm. Okay, it is 97.82 mm. This is our effective depth. Now from assume clear cover and bar diameter and then calculate the overall depth. Here assume clear cover is equal to 15 mm and bar diameter is equal to 10 mm. So clear cover assumed is 15 mm and bar diameter is 10 mm. So calculate the overall depth D now. So overall depth D is equal to effective depth 97.82 plus your clear cover plus half of bar diameter. So how much it is? 117.82 mm. So we will round up this depth to 120 mm. Okay. Now if our overall depth is 120 mm, so therefore again calculate the effective depth as we round up the overall depth. So D is equal to 120 minus 15 minus 100 by 2. Small d is equal to. So it works out to be 100 mm. So our effective depth is 100 mm and overall depth is 120 mm. Okay. So after that, calculate the effective span. Calculate the effective span. So now, what is the effective span? So effective span is nothing but the center to center distance between the support. Okay, it is given on in clause number 22.2.3, page number 35. So we will move to the IS code. So now go to page number 35. This is page number 35. Okay, and it is given in clause number 22.2.3, 22.2.3. This is 22.2 effective span. Okay, so now here you can see this is given for discontinuous support. So this is given for discontinuous support which we have used for the one waistline. Okay, now here you can see for the end span with one end fixed and the other continuous, or for intermediate spans, the effective span shall be taken as clear span between the supports. So here if you see, it is given clearly what you should consider. If you read this, then you will get what is given over here. So the for the end span with one end fixed and other the other end is continuous or intermediate span, the effective span shall be the clear span between the supports. So you need to calculate the distance from center to center of the supports. Okay, what does it says that the distance is center to center distance between two supports. Okay, this is what this says. Now Again we will move to the whiteboard and we will do the further calculations. So here effective span तुम्हाला हे clause number 22.2, page number 35, the 1. What does it say? That effective span, I can directly write now. Effective span is equal to, it is 3 plus left hand side support plus right hand side support, so which is equal to 3.15 meter. 3.15 meter. This is your effective span. This span is your effective span. So now do the load calculation. Next is the load calculation. So how do we calculate the load now? First of all, in the load calculation, we will assume the width of slab as 1 meter. The first thing is that assume width of slab is equal to 1 meter, which is equal to 1000 mm. This is the width of the slab. So now take the self weight of the slab first. Now start calculating the load. So first is the self weight, or you can simply say weight of slab or self weight of slab. It is D is the depth into 1 is the width into 25. So which is equal to, what is our overall depth? 0.12 into 1 into 25. So the answer works out to be 3 kilonewton per meter. This is the weight of the slab. Then weight of floor finish. Okay, dead load मध्ये अजून काय येणार आहे? Weight of floor finish, which is equal to 1 into 1, which is 1 kilonewton per meter. If the value of floor finish is not given in the numerical, assume it as a 1 kilonewton per meter square. Okay. So weight of floor finish. After that, calculate the total dead load. What is the total dead load now? It is 4 kilonewton per meter. Now live load. Calculate the live load. It is 3 into 1, which is equal to 3 kilonewton per meter. Okay. So the total load is equal to how much? 4 plus 3, which is equal to 7 kilonewton per meter. This is the total load. Okay, this is the total load. But see here, what is required here in this design of one-way continuous slab. Now note down, this is very important point. While calculating the bending moment and shear force in the case of this one-way continuous slab, we will the live load and dead load. Total load is not required. Total dead load is required and total live load is required. Again, I will repeat my sentence. While calculating the shear force and bending moment in one-way continuous slab, total load is not required. So what I mean to say, this total load is not required. Okay. So instead of this total load, total dead load is required and total live load is required for the calculation. Okay, total dead load is required and total live load is required for the calculation. Okay, so now instead of taking this, जरी तुम्ही इथं टोटल लिहिली तरी काहीही चुकत नाही, पण लोड कॅल्क्युलेशन करताना आपल्याला टोटल लोड लागत नाही इन द केस ऑफ वन वे कंटिन्युअस स्लॅब. त्याच्यामुळे तुम्ही टोटल केली काय किंवा नाही केली काय, इट डझंट मॅटर. So now see here, this is the total dead load and this is total live load. So now calculate factored dead load. Factored dead load, or it is called as ultimate dead load WD, which is 1.5 into 4. This comes out to be 6 kilonewton per meter. Similarly, factored live load is WL, which is equal to how much it is, 1.5 into 3. So it is 4.5 kilonewton per meter. Now we know the value of dead load and live load. Now just remember this thing, in this type of slab, in the type of one way continuous slab, we don't take the total load, we don't add live load and dead load. Okay, so we have taken it separately. What is the total dead load, what is the ultimate dead load, then what is the total live load and what is the total ultimate load. Okay, so now after this, next part is the calculation of bending moment. Now you know the load. Total dead load is 6 kN per meter. Total live load is 4.5 kN per meter. Okay. So now to calculate the bending moment, again we will go to the IS code. So this is your table number 12. Bending moment coefficients. Now see, before moving to this, I will explain you how the bending moment diagram is, so that it will be clear or not. This is your panel number 1, panel number 2, panel number 3, then 4 and 5. So 5 panels are there. Okay. So now the load is acting on these panels vertically downward. The center to center distance between each panel 3 meter. Okay. So now what we will do, if I want to draw the bending moment diagram of this, then the bending moment diagram will be, here at the support some hogging moment will be there. Here at the support some hogging moment will be there. Then at the center sagging moment is there. Again at this support hogging moment will be there. Okay. This is again at the center sagging moment is there. Again hogging. So this type of bending moment curve you will get in the case of these continuous slabs. So now if I give the name, then this is called as end support. This is also called as end support. These are called as intermediate support. Okay. So if I give the name to the panel, this is panel number 1, 2, 3, 4, 5. out of which panel number 1 and 5 are end panels. Now if you see carefully, at support there is a negative moment, at center positive moment is there. Again this moment is negative, here it is positive. Hugging negative, sagging positive. Again hugging negative, sagging positive. This is also negative, this is positive. Okay. So this is the bending moment diagram for one way continuous slab. Okay. Now, how to calculate the bending moment diagram and what are the coefficients, that we will take in the next lecture. For today, it is sufficient. Now, drop your roll number into the chat box.